Continuing on physical chemistry, chapter 5, we're beginning section 4 now. So how do we measure the standard enthalpy of formation of a substance at 298 kelvins? Well, one is calorimetrically, or calorimetry. We could do it A at constant volume, in which case the change in the internal energy is just equal to Q at the constant volume. We could do it at constant pressure. Then we have the Q at constant volume is just equal to N times the specific heat times the change in temperature. And then the heat capacity is going to be N times the specific heat. Or two, we could do it spectroscopically. Anyway, that'll tell us the bond energies. Three, we could do it Gibbs free energy in the third law using the change in enthalpy minus temperature times the change in entropy is equal to the change in Gibbs free energy. 4, we could measure temperature variation of Kc. Kc is the equilibrium constant. We will be talking a lot more of that when we get to kinetics. For example, in bomb calorimetry, remember bomb means constant volume or isochoric. So in a bomb calorimeter, we have the change in enthalpy is equal to the change in internal energy plus the change in the number of moles of gas times R times T. And change in internal energy is equal to the heat capacity at constant volume times the change in temperature. Now, what is the relation between the change in enthalpy, the standard change in enthalpy, and the standard change in internal energy for a chemical reaction? Well, remember, the naught means the standard state, so the pressure is at 1 bar. So the enthalpy at the standard state is equal to the internal energy at the standard state plus the pressure at the standard state times the volume at the standard state. So that gives us the change in enthalpy in the standard state is equal to the change in internal energy in the standard state plus the pressure in the standard state times the change in volume in the standard state. Now we know the pressure is constant because by definition the standard state is 1 bar. It's a constant pressure. Now we're also going to say constant temperature, and we're going to talk about an ideal gas. So we have the change in enthalpy in the standard state with constant temperature is equal to the change in internal energy in the standard state at constant temperature plus the change in the number of moles in the gas phase times R times the temperature. Remember, R is the gas constant, 8.314 joules per mole Kelvin. And like I said, delta Ng is the change in the number of moles, is the change only for the gaseous state. The number of moles in the liquid and solid don't matter because they don't take up nearly as much space. The change in the number of moles in the gas is equal to the sum over I of the number of moles of I times the gaseous products minus the sum over all the substance I times the number of moles of I times the gaseous reactants. Now the change in the number of moles of G, it actually has no units. It's like the change in of the gas divided per mole. So then the moles cancel out. So the change in the enthalpy in the standard state at whatever temperature is equal to the change in the internal energy in the standard state at constant temperature plus the change in the number of moles in the gas phase times R times temperature. And we just ignore solids and liquids when we do this formula. If we have reactions involving just liquids and solids, then delta N in the gas phase is going to be equal to 0. So we just end up with the change in enthalpy in the standard state at constant temperature is roughly equal to the change in the internal energy in the standard state at constant temperature. Now, even for reactions with gases, this term can actually be kind of small. It's often a lot smaller than the other term. So, for example, let's do ethane gas again, burning with oxygen gas again to give off carbon dioxide gas and water gas. Then the change in the number of moles in the gas phase is going to be 2 plus 1 for the products minus 3.5 plus 1 for the reactants. So delta Ng for the reaction can be 0 though, by the way. So let's say we have 2 hydrogen chloride gas. Remember, it's not hydrochloric acid, it's not aqueous or anything. But anyway, going to hydrogen gas and chlorine gas. Well, 1 plus 1 is 2, 2. So the change in the number of moles in the gas phase is equal to 0. So in this case, the change in the enthalpy of standard state is going to be roughly equal to the change of the internal energy in the standard state. Now for solids and liquids, the change in the enthalpy in the standard state is equal to the change in the internal energy in the standard state. Now for gas, the change in the number of moles in the gas phase times RT is usually about 2.5 to 8.3 kilojoules per mole. So the change in the enthalpy of formation is going to still be roughly the change in the internal energy. Just because this last term is so small, we can just ignore it. Now let's talk about Hess's law. The overall reaction enthalpy is the sum of the reaction enthalpies of the individual reactions into which the reaction may be divided. That's because enthalpy is a state function. For example, let's say we're doing a reaction. We're going from reactants to products. Well, we decide we're going to do it in a whole bunch of little baby steps. It doesn't matter how many steps you divide it into or how you divide it. If you still start out with the reactants, you end up with the products. Enthalpy is a state function, therefore the change in enthalpy must be the same. So here are some examples. Here we are with ethane again and oxygen going to carbon dioxide and water. So the change in enthalpy, I don't know why I wrote 1. Oh, it must be equation 1. In the standard state, so that is going to be minus 1,560 kilojoules per mole. So for equation 2, we're going to take carbon in the graphite form plus oxygen and burn it to get carbon dioxide. So the enthalpy of formation, or the enthalpy of the reaction, the change in enthalpy in the standard state for equation 2 is going to be minus 393.5 kilojoules per mole. And then hydrogen, burning that with oxygen to give water liquid, that's going to be minus 286 kilojoules per mole. But what is the enthalpy of formation at 298 kelvins in the standard state for the ethane gas? Well, let's say we have 2 carbon in the graphite form plus 3 hydrogen in the gas form going to the ethane gas. So how do we find this? Well, first we need to double the middle equation. So we're going to get 2C. Oh, I see, these 3 are givens, and we're going to use this to find this. Okay, this is all the same example. So we're going to, where was I? We're going to double this equation so we end up with the right number of graphites. So we're going to take 2 times the graphite plus 2 O2 gas goes to 2 CO2. And just for doing that, we get 2 times negative 393.5 kilojoules per mole. Likewise, to end up with the right amount of water, 3 water, or no, why is it? Oh, hydrogen. To use up the right amount of hydrogen, we're going to take triple the bottom row. So we're going to take 3 times H2 gas plus 3 halves O2, going to 3 H2O liquid. So we're just going to take 3 times that number. So we get 3 times negative 286 kilojoules per mole. And then finish up, we're going to actually take the reverse of the top equation. So we're going to take 2 CO2 gas plus 3 H2O liquid going back to ethane and the oxygen. So our change in enthalpy for step 3 is going to be a minus 1 times that negative 1560 kilojoules per mole. So now we add those up and cancel the like terms. We end up with what we wanted, 2 carbon graphite plus 3 hydrogen going to ethane. That'll get, so the total enthalpy is a state function, so we just add it up. The change in enthalpy is going to be the change in enthalpy for step 1, step 2, and step 3. And that gives us just negative 85.0 kilojoules per mole. That's the end of section 4.